This research delves into the entropy of rectifiable and stratified measures, rooted in geometric measure theory. It first examines the entropy of rectifiable measures, elucidating their properties in relation to the Hausdorff measure. Notably, these measures exhibit a Hausdorff dimension, which is preserved under Lipschitz transformations. The concept of stratified measures is then introduced, defined as convex combinations of rectifiable measures. This generalization of discrete continuous mixtures allows for a singular continuous part, enabling the modeling of complex structures. The entropy of stratified measures obeys a chain rule, where the conditional term is an average of the entropies of the involved rectifiable measures. This chain rule is a fundamental property, as it enables the decomposition of entropy into its constituent parts. A crucial aspect of this research is the asymptotic equipartition property, AEP, for stratified measures. This property demonstrates concentration on strata of a few, typical dimensions, and links the conditional term of the chain rule to the volume growth of typical sequences in each stratum. The AEP is essential for understanding the behavior of entropy in these measures, as it reveals the underlying structure of the entropy landscape. In geometric measure theory, the Hausdorff measure is a crucial concept that extends the classical notions of length and area to higher dimensions. This measure is defined as an outer measure, restricting to a measure on the Borel sigmalgebra, with the property of being sigma additive. It is a natural extension of the Lebesgue measure in Euclidean space, providing a general framework for understanding m-dimensional volumes. The measure him, when m is an integer between 0 and d, gives rise to a notion of m-dimensional volume, which coincides with the classical notions of length and area when m equals 1 and 2, respectively. This concept plays a pivotal role in differential geometry, where Lipschitz maps serve as a generalization of smooth maps, and rectifiable sets are a generalization of manifolds. Geometric measure theory also has significant implications for the calculus of variations, where it is used to understand non-smooth objects and their properties. The theory provides a powerful tool for studying these objects, allowing researchers to quantify their size and shape in ways that traditional methods cannot. Moreover, the Hausdorff measure can be used to define the dimension of a set, providing a more nuanced understanding of fractals and other non-integer dimensional objects. This measure has far-reaching applications in various fields such as physics, engineering, and computer science, where it aids in modeling complex systems and understanding their properties. In conclusion, the Hausdorff measure is a fundamental concept in geometric measure theory, providing a general framework for understanding m-dimensional volumes and extending classical notions of length and area. Its connection to differential geometry and its importance in the calculus of variations make it a crucial tool for researchers across multiple disciplines. The concept of Hausdorff measure and dimension is introduced, focusing on rectifiable sets and their application in computing integrals. Hausdorff measure him, A, is defined for a set A in Rho, which can be either 0 or infinity, except for a specific value of m, called the Hausdorff dimension dimma of A. The measure interacts naturally with Lipschitz maps, as shown in Lemma 1, where the measure of the image under a Lipschitz function is bounded by the product of the original measure and the Lipschitz constant. The paper then discusses m-rectifiable sets, defined as the image of a bounded subset under a Lipschitz map, and countably m-rectifiable sets, which are countable unions of m-rectifiable sets. An example of a countably m-rectifiable set is an m-dimensional C1 submanifold east of Rho. For every countably m-rectifiable set E, there exists an H-null set E0, compact sets key, and injective Lipschitz functions phi such that E is contained in the union of E0 and the phi key. This implies that every m-rectifiable set has sigma finite measure, and any subset or countable union of m-rectifiable sets is also m-rectifiable. The area and CO area formulas are introduced for computing integrals on nm rectifiable sets with respect to the measure, involving the area and CO area factors defined using linear maps between finite-dimensional Hilbert spaces. The section begins by defining the Jacobian factor as the square root of the determinant of the transpose of a linear transformation L, under the condition that the dimension of the domain V is greater than or equal to the dimension of the codomain W. The CO area factor is defined similarly, using the determinant of the linear transformation L itself. The area formula, also known as proposition 2, establishes an equivalence between integrals over subsets of the domain and integrals over the corresponding subsets of the codomain through the Jacobian or CO area factor. This is demonstrated through examples of curves and surfaces, illustrating how the formula can be applied to compute lengths and areas. The section concludes by highlighting the utility of computing integrals over countably rectifiable sets through iterated integrals, including a mention of Fubini's theorem as a special case. The concept of rectifiable and stratified measures is central to geometric measure theory. It begins with the CO area formula, a fundamental tool that states for a Lipschitz function f r⁻k right pointing arrow r⁻d, a countably h⁻m rectifiable subset E of r⁻k, and a Borel function g r⁻k right pointing arrow 0 infinity. The set E intersection f⁻1 t is countably h⁻md rectifiable and h⁻md measurable. This formula is crucial for understanding the properties of measures and their applications. The concept of disintegrations, a generalization of Fubini's theorem, is also discussed. A measure nu has a t(xi) disintegration if it can be decomposed into a family of measures nu_t, such that each nu_t is a sigma finite measure on B, and for any non-negative measurable function f e right pointing arrow r, the map t right pointing arrow underscore ef x d nu_t x is measurable, and underscore ef x d nu x equals underscore e caret t underscore ef x d nu_t x d xi t. The definition of rectifiable measures, introduced by Marstrand and refined by Price, is also key. A radon outer measure nu on r⁻d is called M rectifiable if nu much less than h⁻m and there exists a countably h⁻m rectifiable Borel set E such that nu r⁻d E equals 0. This concept plays a significant role in understanding the structure of measures and their properties in geometric measure theory. The study of M rectifiable measures from an information-theoretic perspective focuses on the properties of the entropy HHM ρ of an M rectifiable probability measure ρ. An M rectifiable measure nu is absolutely continuous with respect to the restricted measure hm E** operator, where E** operator is countably M rectifiable and has the form n airy union I element of n phi key, with phi injective and key Borel and bounded. A refinement of this construction yields a similar set where the density of ρ is strictly positive. Carriers of M rectifiable measures exhibit desirable properties. If C is a carrier of an mi-rectifiable measure nu I, for I equals 1, 2, then S1 times S2 is a carrier of nu 1 circled times nu 2, with Hausdorff dimension M1 plus M2. Moreover, the Hausdorff measure hm1 plus M2, S1 times S2 equals hm1, S1 circled times hm2, S2. Let ρ be an M rectifiable measure with carrier E, then ρ much less than hm E and hm E is sigma finite. If, in addition, HHM E ρ less than infinity, proposition 1 provides estimates for hm E circled times n w n delta ρ hm E. Furthermore, n is Mn rectifiable and hm E circled times n equals HMN n, which is desirable since the Hausdorff dimension of n is Mn and Hmn is the only non-trivial measure on it as well as on W n, which is Mn rectifiable. To apply the asymptotic equipartition property, we need to compute HHM E ρ. In some cases, the area formula can be used to change variables and express HHM E in terms of the usual differential entropy. For instance, if A is a bounded Borel subset of Rk of non-trivial Elk measure and F is an injective Lipschitz function on A, then the set F A is rectifiable. Furthermore, if ρ is a probability measure such that ρ much less than Lk A with density R, then the area formula shows that F** operator ρ much less than Hk F A with density R, JKF ring operator f-1, which is well defined, hk, f, a, almost surely. A simple computation yields hhk, f, a, f asterisk operator rho, equals hlk, rho, plus east rho, lane jkf. Finally, we deduce the chain rule for the entropy of rectifiable measures as a consequence of our general theorem for disintegrations. Let E be a countably, m, rectifiable subset of Rk. F. Rk right-pointing arrow rho a Borel function, with D is less than or equal to m, and rho a probability measure such that rho much less than E. Then F asterisk operator rho much less than LD, and HHM, E, rho, equals HLD, F asterisk operator rho, plus integral RKHF minus 1 minus D, E intersection F minus 1, T, rho T, DF asterisk operator rho. The authors delve into the entropy of rectifiable and stratified measures, reformulating the integrand in equation 13, using the chain rule for the Radon-Nikodym derivative, which recovers the formula 50, in reference 7. A k-stratified measure is defined as a measure nu that can be expressed as a sum of k-rectifiable measures, each with a different dimension. A fundamental example is a discrete-continuous mixture, corresponding to k equals 2. A stratified measure has a Lebesgue decomposition with a singular continuous part, provided some dimensions are strictly between 0 and d. Consider a probability measure ρ that is stratified, which can be put in the standard form as a mixture of k-rectifiable probability measures, each with a carrier of different dimension. The carriers can be taken to be disjoint, and the measure ρ can be regarded as the law of a random variable x valued in the union of the carriers. The vector of weights can be seen as the law of a discrete random variable y, and the authors define the random variable d as the dimension of the Hausdorff measure of y, with expectation E, d, being a weighted sum of the dimensions. The measure ρ is absolutely continuous with respect to a mixture of Hausdorff measures, and the authors define the entropy h micro ρ in terms of the entropy of the weights and the entropy of each rectifiable measure. Notably, the entropy has a concrete probabilistic meaning and can be expressed as the sum of the entropy of the weights and the weighted sum of the entropies of each rectifiable measure. This formulation enables the exploration of the intricate relationships between the entropy of stratified measures and the properties of their constituent rectifiable components. Stratified measures offer a novel approach to understanding the structure of measures on product spaces, introducing a chain rule for general disintegrations. This rule is applied to stratified measures, yielding a refined version of the asymptotic equipartition property, AEP. The AEP, a fundamental principle in information theory, describes the behavior of entropy as the number of realizations increases. The authors extend this principle to stratified measures, providing a nuanced understanding of entropy behavior in complex systems. Central to this approach are doubly typical sequences and strata, subsets of realizations with specific properties. These subsets approximate the original measure with arbitrary accuracy, allowing for better control over the dimensions appearing in the approximation. The conditional entropy H, X, Y quantifies the volume growth of most doubly typical fibers, providing a quantitative measure of system complexity. This result has implications for understanding entropy behavior in information theory, statistical physics, and machine learning. The refined AEP and doubly typical sequences provide a more precise understanding of the structure of measures on product spaces. This work contributes to the advancement of information theory and its applications in various fields, offering a powerful tool for analyzing complex systems. In the realm of information theory and geometry, the authors have established a profound connection between the entropy of a measure and its geometric properties. This connection is encapsulated in the limiting property of the set B, n, epsilon, which is defined as the set of y element of A, n, delta, such that 1, n lane y, t, n, delta, y, greater than h, x, y, epsilon plus delta, n. The property states that as delta in, right pointing arrow 0 and n right pointing arrow infinity, we have lim sub 1, n lane, b, n, epsilon, equals h, y, equals lim sub 1, n lane, a, n, delta n. This result provides a geometric interpretation to the possibly non-integer dimension E, d, equals n array summation ki equals 1 qimi, which under suitable hypotheses is the information dimension of ρ, as discussed in 13, sec. v. This answers an old question posed by Rainey in 10, page 209. The author's work builds upon a range of existing research in information theory, geometry, and measure theory, citing key contributions from Alberti et al. 1. Ambrosio et al. 2. Cover and Thomas. 3. Sischer and Corner. 4. Delelis. 5. Federer. 6. Koliander et al. 7. Montilla. 8. Morgan. 9. And Rainey. 10. The paper's results are also connected to recent work by Vigneaux, 11, 12, 13, which explores the relationships between entropy, geometry, and information theory. Overall, this research provides a significant contribution to the understanding of the entropy of rectifiable and stratified measures, shedding light on the intricate connections between geometric properties and information theoretic concepts.